Okay. Yeah. So it's really a pleasure to be here. I've heard from my Lithuanian colleagues a lot about the Life Sciences Center here, and so I'm excited to be able to talk with you, and I hope I'll have a chance to hear from you while we're here together. So yeah, my name is Pietro Michelucci, and so my background is actually in cognitive science. I'm not a biologist, and so I took all the slides related to biology out of my talk because I realized that I would likely get into big trouble, and so I will only spread misinformation about biology in other talks, but not this one. Also, I realized that the scope of my talk seems a little narrow. I originally considered including the multiverse, but I thought it would be appropriate to manage the scope to just our own universe. So I hope that's okay. So what I'm going to talk about, a little bit about the history of information processing and what that means. And then the idea of bringing humans into the information processing loop. And then finally, what the coevolution of humans and technology and the implications for that in our future. So it's kind of a past, present, and future look. And much of what I'll be talking about is actually speculative, and the idea is really to begin a conversation and to think about some of these concepts together. So to begin with, start at the beginning. We had the Big Bang, and then 4.5 billion years ago, approximately, we had the formation of the Earth, and of course, at that time the Earth looked a little more like this. And then about 3 billion years ago, we believe that we had the first signs of life. The thesis here is that life represented the first instance of information processing in our universe. So why does life represent information processing? Well, you might be able to imagine that there are all kinds of information being processed in organisms. Reproduction itself involves complex information processing. And the earliest organisms were able to respond to the environment, to various forms of stimulation, light, and chemicals, and magnetic fields. And so as we think about information processing coming from the behavioral sciences, does anyone recognize who this person is? No. So that's B.F. Skinner, who started the behavioral revolution. And his idea was, we're really not so much interested in what happens inside the system. We want to look at what goes into the system and what comes out. And that was useful for a lot of applications. But then someone had what I think was a good idea, which was to actually investigate what's going on inside this black box. And that was the beginning of the cognitive revolution that continues today. So when we look inside some of these early organisms and say, well, how was the information being processed? Then we start to understand that there's a sensory process, there's a decisional process, and we start to get an idea of the components of information processing. So, in a simple bacterium like that, then you can imagine again that there's a receptor state, and if it's activated, then that suggests one action, and if it's not, then there's another action. Very simple. So over time, we've evolved specialized cells to do information processing that work specifically for this purpose. For example, neurons in the brain. Although before the neurons evolved, some of the other types of cells were repurposed. And there are some organisms today that continue to do information processing without neurons. But the question is, as we see this evolution of intelligence in animals, it raises this question of what's the evolutionary basis? What's the survival advantage of having intelligence? So before we can answer that, it sort of makes sense to think about what do we mean by information. So in English, information comes from the word, or is related to the word informative. For something to inform us, it's not something we would be expecting. So one of the things I've really enjoyed in my first time in Lithuania is these chocolates that you have. I don't know if I'm saying it right, the sostinas. And when I first tasted one, I thought, well, this is going to taste like chocolate. I didn't know exactly, that was my model of chocolate. It looks like this, it tastes like chocolate. And then something wonderful and unexpected happened, and there were other flavors in there. And so that informed me, and so the next time I had one, I had a better idea of what to expect, and I could make a better choice, which in my case was to continue to have more of them. So here's a very simple process model about the value of prediction. So you walk into the woods and you see an animal you've never seen before, and you have a few choices. Is this a danger, or is this food? And you have so you make a prediction about this. If your prediction is consistent with what happens, then you might live to see another day. You make the right decision, it's dangerous, and you run away. And that reinforces your model. So next time, you're more likely to engage in the same behavior. If you make the wrong decision, and you happen to survive making the wrong decision, then that will revise your model. Now you have a new model, and you might make a different decision next time. So that's a very simple model. But what are the benefits of more sophisticated models of information processing? So as we encounter a wider variety of circumstances and or challenges related to our survival, then it's beneficial to have a more sophisticated and more complex ability to process information. So traditionally, we think of information processors, like this. If you go and look at a job board and they're looking for an information technology professional, they're not usually looking for a mammalian brain. They're looking for someone who knows how to operate this kind of machinery. But there are different kinds of information processors, and those are the ones we've invented to do the kind of work that we're not very good at. But then life processes also give us an affordance, give us a kind of information processing capability. So now I'm going to talk about this idea of human computation. So the human brain today is the most complex information processor in the known universe. We have 100 billion neurons and approximately a quadrillion connections among these neurons. And having such a complex processor has allowed us to invent things. And the combination of inventing these new capabilities and powerful technologies with our collective behavior as humans has actually created new problems. So we've solved problems, but now we have more challenging problems. So for example, in the life sciences, we've developed biomedical technologies and solutions that have allowed us to live longer, but this creates the problem of overpopulation. And then in engineering, we've figured out how to build aircraft, which allows us to fly all over the world. And these two new capabilities create a situation where you have many more people closer together, so there are opportunities for viruses to spread more quickly and recombine and mutate. And then those viruses can easily travel to many different places. So now, how do we solve this problem? And in some ways, that's potentially a more difficult problem to solve. So how do we do this? If we don't, as individuals or coordinated groups, are not able to solve these problems, then maybe we try to make a machine that's smarter than we are to solve this problem. So one idea that you hear from the artificial intelligence community is, as soon as we can just figure out how to connect a computer to a brain, then we can upload the brain into the computer and we can speed it up and make it go many times faster. But does faster necessarily mean smarter? So in human computation, we have this other idea, which is, what if we leverage human computation in a network that includes humans and machines? So here we're trying to look at the complementary abilities of both of these in order to create capabilities that couldn't exist independently. In other words, we want to be able to do things that machines by themselves cannot do and that humans by themselves cannot do. And is there some way of combining these capabilities to do that? So the way we approach this is, first we need to say, well, what are the things that the machines do well? So machines are obviously very good at counting and remembering things, following a logical process. And then what do the humans bring to this conversation? Humans can do inference and visual perception. We have language. And you might sense an ordering here. So at the higher levels of cognition, we have abstraction. We have experiences that lead to world knowledge and social cultural awareness and creativity. So this suggests kind of a continuum. And anyone who follows artificial intelligence research might realize that over time we're gradually annexing these human capabilities. But one of the things we find is that as we climb, or in this case descend this ladder, each of these becomes increasingly difficult. So while there might be this sense in the media and even in the scientific community today that AI research is accelerating, it's actually slowing down with respect to human capabilities. An interesting question about this is what would be the impact on human labor? And there's concern that, well, AI is going to take away our jobs. And I think another perspective is to look at the Industrial Revolution and say, well, bringing machines into factories actually created new kinds of jobs that were potentially more interesting and fulfilling. Instead of being the machine in the factory, we became the inventors of these new machines. So human computation is about finding the right partnerships in order to derive value from machines and humans working together. And one flavor, if you will, of human computation is emergent human computational systems. So this represents a social network, like a Twitter activity. And so we didn't create Twitter in order to do information processing. But if you analyze the activity on a Twitter network, you can gain information that you might not otherwise have. You might be able to make predictions about events in the world, or you might be able to learn something about social behavior. One example of this kind of emergent behavior is during the flu season, people tend to go into Google and say, what about this symptom if I have a runny nose or a sore throat? And so there was a study done that compared this activity on Google with the Center for Diseases Control in the United States and their prediction of the spread of influenza. And it turned out that the Google queries actually, in some cases, anticipated. They were at least as good as the CDC predictions. But I'm going to talk a bit more about engineered human computation systems. These are systems we build for a specific purpose. So this is something that you're probably quite familiar with. Most of us have been part of this crowdsourced labor. So, of course, the idea here is that if you want to prove that you're not a web bot and get into a website, that you have to type these distorted snippets of text. But what some people don't realize is that the reason there are two words is that one word is known already, and that's to make sure that you're not the web bot and that you're doing this correctly. And the other word is taken from a piece of text that we'd like to digitize. So the original reCAPTCHA took 100 years of archived issues of the New York Times and then digitized them all through this process. So anyone who participated in this when it was first on the web helped to digitize the New York Times, and you can contact Louis von Ahn if you'd like to get paid for your labor on that. So the same scientist who developed reCAPTCHA created Duolingo, and this is another quid pro quo. So it's great, for learning new languages, but at the same time, when you reach a certain level of capability, then you're actually your lessons are helping to translate documents from one language to another. So another brand of human computation is called citizen science, and this is the idea that the quid pro quo, the value that a user gets from participating is that they can learn about science and they can make a meaningful contribution to the advancement of science. So a popular platform for this is called Zooniverse that you may have heard of, and you can participate in a project where you help to classify galaxies and do different kinds of analysis. And then SciStarter is another way to find projects of all different types in different areas of science. It's kind of like a search engine for citizen science. So one interesting example of citizen science, this was one of the pioneering projects in 2006, was so NASA took a spaceship and flew it through the tail of a comet. And they had these collector grids that would capture the dust. So they're filled with aerogel, which is the least dense substance that we know of. And then they brought these collector grids back to Earth. And the idea was, okay, now we have to find these interstellar dust particles to help inform our models of cosmology. And the problem is they were only expecting to find a few of these, and I think there were about 1 million images of the aerogel. So they estimated it would take about 100 years for the scientists to scan through all these images. So the PI on this project, Andrew Westphal, knew about this other project that preceded it. And depending on how old you are, you might remember, this probably still exists today, but the SETI at home was a screensaver. This was in the days when we had CRTs and the screens would burn an image in if you didn't keep changing what was on the screen. So they decided to take the need for a screensaver and use it as an opportunity to borrow labor from computers all over the world. So you contribute your computing time when you're not using your computer, and you get to be part of an exciting search for signs of extraterrestrial intelligence. And so both of these projects, the Stardust at Home and SETI at Home, were both out of Berkeley. And Andrew knew David Anderson, who had done that, and he went and he said, hey, look, this thing you did with distributed computing or volunteer computing, can we do this with thinking? Can we actually distribute the labor of looking at these pictures of aerogel to find those interstellar dust particles to thousands of people and try to make quick work of this? So that's exactly what they did. They collaborated on this, and I guess this is actually a movie. I didn't realize. So they created an interface they call the virtual microscope. And I'm just going to run this a few times. So you can see where it says track. That's a dust particle track. And so humans are shown what these look like relative to other artifacts. So everything else you see is just an artifact of the aerogel. but this has a kind of persistence that's different. And at the time, and possibly today, this would be a difficult thing to train a machine to do. But the humans were able to do it, and they created an online platform and engaged 30,000 users to do it. They found 7 interstellar dust particles and published their results in Nature, I believe. And they included all 30,000 volunteers as co-authors on the paper in Nature. So more recently, at the Human Computation Institute, we saw an opportunity to solve another kind of problem. So I was introduced to a biomedical researcher at Cornell University who was doing Alzheimer's disease research. And he and his colleagues invented a new imaging technology that would allow live brain imaging of a mouse at different levels of brain tissue. And then the idea was they were investigating the role of brain blood flow in Alzheimer's disease. So this is an aspect of the disease that's been known about since the beginning of Alzheimer's, but no one has ever understood the role of blood flow in the brain. So they were interested in answering this question, but they created kind of a big data problem. Their new method of gathering data resulted in a data set that was very time consuming. So it would take, to answer one research question, would take an entire year for the lab technicians. So when this was described to me, I asked to see exactly what it looked like, the kind of images and the videos, and what were the lab technicians doing that was taking so long. When he showed me what they were doing, I realized that this was something that, like the Stardust at Home project, we could possibly crowdsource. And in fact, I got very excited because, as you can see from this image of the blood cells, or of the blood vessels in the brain, that there's a similar kind of perceptual aspect to looking through aerogel and looking at blood vessels in a mouse brain. So we created an online game called Stall Catchers that allows people to participate in this analysis, and we've reduced the expected time to potential treatment from decades to maybe only a few years. And so also I'd like, when I say we, I gratefully acknowledge Agla Maria Ramnauskite, who's hiding somewhere in the right in front of me, who co-founded this project with me, and then Vika, I'm not going to say your last name right.
Okay.
Sorry.
So
who recently also joined our project. So there are other examples. I should be careful about the time. I won't tell you about all of them. I'll mention Galaxy Zoo. This has been a popular one. Has anyone here participated in Galaxy Zoo? One? The astrophysicist in the room, of course. So this is fun. You go online. They teach you what the different galaxies look like, and then they have the Deep Sky Survey. So again, lots of pictures, not enough time, but it's easy to teach a person how to classify a spiral galaxy or a barred galaxy, and so with many people involved, we make short work of that. But a very interesting thing happened with the Galaxy Zoo project. One of the volunteers found a galaxy that didn't fit any of the existing classifications. And there was a forum, so the volunteers self-organized, and they started talking, saying, hey, did you see this? This doesn't look like anything else. What is this? And on their own, they started looking at the research papers, and they finally believed that they had discovered a new kind of galaxy, and then they showed their results to the scientists. And in fact, it was a completely new discovery made by the volunteers. So the common question is, what do humans bring to the partnership? And so this game, Philo, is about it's about trying to identify similarity between different DNA segments, and similarity is defined in a very specific way. So they made it into a game. And so this is the sort of thing where you might say, well, why couldn't you just use a computer to sort of go through all the combinations? And there are certain classes of problems in computational complexity theory that are called NP-hard. So the idea is that as you increase the number of possibilities, the combinatorics explode, and it would take hundreds of years of computing time. So what humans tend to be good at doing is excluding the things that don't matter. When we're trying to solve a problem, we immediately rule out lots of things that seem obvious to us. Oh, it could never be this, it could never be this. Doesn't mean we're not wrong sometimes. But for certain classes of problem like this one, the humans can get to a solution faster. This is another kind of engineered system, a virtuous ecosystem. So this is from patients like me. The idea is that if you have a disease, then you go to this website and you find a community of other people who have the same disease. And each person enters in information about their own treatment experiences. And this information is aggregated. And then this graph is kind of a nice idea. So here, each dot represents a different treatment. And it's the x-axis is how popular, how many people have used the treatment, and then the y-axis is how effective do they report that treatment was. So if you have fibromyalgia and you've tried some treatments and you've been frustrated, you might notice that, well, there's this treatment up here that looks extremely effective, but only a few people have tried it. But then when you click on it, it's something very simple, like taking a cold shower. And you think, well, that doesn't cost too much. I can try that. But then the virtuous ecosystem, this idea of kind of a virtuous cycle comes into play, because after you try that, you're inspired to try it, then you bring your new data into the system. So you start to cluster experiences around the things that potentially look promising. And all of these data are shared with pharmaceutical companies as well. And everyone who participates in the system knows about this. So the internet has obviously enabled us to connect a lot of people. And now there's this opportunity that where we run into physical barriers to collaboration, those start to disappear. So this kind of takes us to the next step. Well, let's say we can get 1 million people into a virtual room. How do we actually get them to coordinate their problem solving in a non-chaotic and useful and effective way? So there's this interesting study out of, I think this was MIT and CMU collaboration about collective intelligence. So they were looking at team intelligence or group intelligence. And intelligence in this case was defined as the ability to solve a problem as a group. So we have Team A, and Team A had these individual IQs of the people on that team. And their problem-solving IQ, their group IQ, was 105. Team B had these individual IQs, and their problem-solving IQ was substantially higher and significantly higher. So you ask why. And if you look at the connections between the people in the group, connections in terms of social intelligence, then what they found is that the people in Team A did not exhibit social intelligence the way they were measuring that. But the people in Team B had these more effective connections. They were able to work together more effectively. So this was kind of inspiring, this idea that when you start to build a collective intelligence system, it may be that the connections are as important or more important than the individuals participating in that system. And here's a great example of that. The Netflix challenge happened, I don't remember how many years ago now. Does anyone remember this or have heard about this?
We don't have Netflix.
Oh, you don't have Netflix, okay, but you have something like Netflix.
We have now.
We do have Netflix?
Yeah, but it came here like 2 years ago.
So does your system have a recommendation? Like if you like these movies, you might like these movies. Netflix had the same thing, except it wasn't very good. In fact, I complained about it to the founder of Netflix. So they decided to try to fix that problem by creating a competition, a challenge. And so all these machine learning researchers got involved. And the idea was, if you can create a better predictor of what movie I will like above a certain threshold, we'll give you $50,000. Okay, so all these teams piled on, and they wanted the money and the glory. It's very hard to break until someone breaks it. So they got very close, and finally someone actually broke the barrier for the 50K. Now the way the rules work is if you break that barrier to win the 50K, everyone else has 24 hours to go beyond what you were able to accomplish. And sure enough, this started happening. As soon as one team did better, then the other team started doing better because the collective belief changed. Oh, it's possible. And then at a certain point, it looked like one team was going to win. So all the other teams got together and they said, hey guys, if we don't do something, these other folks are going to win. And they combined their approaches. They got a much better approach, and then they got up to this other prize. If you get to this next level, you get $1 million. Well, when all the other teams saw that, the other teams started grouping together too. So then it became a battle of these groups. And eventually, one team ended up winning the $1 million challenge, but it wasn't the first team that had grouped. So they learned from the other team, and they were successful with it. So I love that example. And I had some nice things to show you as I went. So, one approach to engineering a collective cognitive system is what I call massively distributed problem solving. So we get millions of people to all put their heads together and try to solve a problem, but how do you go about that? So there could be a million ways to do it. We don't know what the right way is, but some of these pieces I've shown you are intended to lead us in the right direction, or narrow that search space. So one approach is to say, well, we have the way things are today, and we have the way that things want to be. So let's give people the opportunity to create some ideas in this space. So someone might suggest an intermediate state. If we want to go from climate change to climate stability, then before we can get there, we actually need to reduce the rate of climate change. So these are intermediate states. And then to reduce that rate, maybe we need to engineer some kind of organism and release it in the atmosphere to do something to the gases in the atmosphere. We need to paint all our roofs white to reflect the energy back. I'm making this up, but to give a collaborative space for ideation, and then opportunities for people to potentially consider and vote on other people's ideas and pull different ideas together to create new ideas. Another application of human computation, and I think all this other stuff in some sense supports this idea, is science is the way that we improve our model of the world. So going back to that original idea of why did intelligence evolve? If we can make a better predictor, we can survive. We have a better chance of surviving. And in some sense, science is about that. Sure, we all want to understand the world better. We have a sort of a natural curiosity. But the practical benefit of science is that if we have a more faithful model of the physical world, then we can make more informed solution ideas, and we can even anticipate better whether a certain solution might or might not work. So one idea here is, how do we involve more people in the scientific enterprise? And many scientists are skeptical about this, and I don't blame them. As soon as you start letting other people tinker with different parts of the scientific process, things could potentially get a little tricky. But what we're finding is there are actually ways to do this, and as long as we understand the contributions that people make, and what the parameters and the error rates and things are, that we can extract useful benefit from that. So today, when we tend to take a linear approach. Here's my hypothesis, and I walk through these steps: methods, experiment, data, analysis, results. But what if we open this up and allow others, make it completely transparent, and allow others to branch off new avenues of exploration based on the same original hypothesis, and then generate new hypotheses based on these results, rather than it all being from the same sort of researcher. We can imagine that certain parts of this process, the ones that involve oversight of the scientific method might best be controlled by scientists, although many aspects of the scientific process could be automated. I mean, it's a method, and it's very well defined in some sense. But the role of the scientist, of course, remains the subject matter expert and the one who can see these problems that can't be easily described to a machine and intervene in the right ways. But possibly some of these other aspects, like carrying out an experiment or analyzing data, could be done by non-scientists. So, getting back to this original question, as we develop further these capabilities of human computation, how do we go about creating a superhuman intelligence? Is problem solving the only measure of superintelligence? So in cognitive psychology, there are folks who build cognitive architectures. So what they're trying to do is take functional aspects of cognition and then build a computational model and trying to replicate what cognition does. But what if we started taking the components of these computational models of cognition and replacing them in different ways with machines and humans in different spots where it makes sense to do that? Could we potentially create something that's more intelligent than we are individually? So that's a question. That's one of many possible approaches. But the one I think I'm most excited about is this idea of collaborative modeling. So, and maybe that's one example of how we would do that. But I think today we have Wikipedia, which is a collection of documents. And it's a collaborative system, but those documents are static. And it's hard to test a hypothesis against a bunch of documents. What if we had something like Wikipedia that was actually a predictive model to which we all contributed our different expertise and abilities? And we built this out so that we could actually predict what's going to happen next in the world and test ideas in that model. So I think this is one vision for a way we could approach this problem of working together for the betterment of society. This is just, with any new technology, there are risks. If you're talking about a collective intelligent system, then just like any intelligent system, there's the possibility of dysfunction or psychopathology, if you want to carry forward the metaphor. And so, in the future, there might be the need for a psychologist who helps collective systems. So I want to tell you quickly about this thing that we call organismic computing. I'm actually jumping ahead. So before I do that, so quickly we talked about the engineered systems. We've talked a lot about the collective reasoning, but there's also this aspect of distributed sensing in human computation. So this is an example of collective sensing. This is the one about the CDC versus the Google analytics, and people observe themselves and other people, and in some sense that's a form of collective sensing, and then we see the aggregate behavioral data. So another variety of distributed sensing is using people as sensors themselves. So they use their perceptual apparatus to go out and count bird species and things like that, and then report that. And then and that's through subjective observations. And then there's this other flavor called participatory sensing. And here we're really just kind of the vehicles that carry around the sensors. And it's just because we move around in the world that makes that useful. So we have the collective reasoning, and we have the shared sensing. And then another form of human computation is coordinated action. That is, by maintaining an awareness of each other, that different components of a system can behave effectively as a group. And we have examples of this in nature, and we have engineered examples. So there's this idea of a wicked project, and so this is part of the Wikipedia project, but the idea is that by coordinating behaviors within Wikipedia, that rather than just having people add little bits of text from time to time, that you could have more effective and more accurate documents, and I think that this has shown some success. So organismic computing is this idea of building a system that's inspired by organisms. So it has all three of these built in at once: shared sensing, collective reasoning, and coordinated action. And so a key idea here is going back to this notion from the group intelligence theory that it's the connections that are important. And each time you add a person to a group, you have, by a power law function, many more connections than people. And so with a small group with 9 people, you might have 78 pairwise relationships. With a medium-sized group of people, 700, and with a large group of 81 people, all of a sudden you have 6,000 connections. So, but this raises the question of how many connections of the possible connections are actually effective. What kinds of connections should you have? How should they be used? So we ran a study, and we created an online game. It was a simulated augmented reality. So that's kind of a strange term. The basic idea is that augmented reality overlays a virtual layer with the real world layer. So you look through something, you see the real world, but you also see artifacts imposed on the real world. I think there are some mobile phone versions where you hold up your phone at a restaurant, you see the restaurant, and then you see all the Yelp ratings. I like this restaurant, I didn't, that kind of thing. So we're imagining a more sophisticated version of this, and it's a hide and seek game. And the basic idea is that with these small, medium, and large groups, we're going to give 3 different levels of engagement among the people in the group to test qualities of connection. And I won't go into the detail now about, it's only important to know that as you go from the radio group, which is really just kind of chatting with each other, up to the organismic group, you have the shared sensing, collective reasoning, and coordinated action all together. That we expected that with the smaller groups, where you're not managing as many connections between the people, it wouldn't be as important. And in fact, it turned out that having the more sophisticated augmentation through technology actually reduced the performance of the smaller groups because there was a learning curve and so on. And then with the medium-sized group, we had this kind of intermediate aspect of sharing information, kind of like a static Wikipedia that they could use in this hide-and-seek game. And in that case, we found that that for a medium-sized group, that turned out to be, it was not as difficult to learn as the organismic, but it gave enough of an advantage at a per connection level to make a difference. But with the very largest group, we found that having this shared sensing, collective reasoning, and coordinated action for 100 people suddenly made that larger group much more effective than any other forms of connecting and augmenting group collaboration. So our actual results very closely mirrored our expected results, with the exception that the organismic result was even more prominent than we expected. Okay, I want to make sure I can hear from you, so I'm going to try to speed up a little. So this notion of interconnectedness I've been discussing in the context of space, but across time seems to be equally relevant. So the persistence and growth of our technology, of course, was enabled by written communication. The ability to transfer this invention from this generation to the next generation, and to do it without loss of information, and so the increasing sophistication of these tools has allowed us to increase the rate of the coevolution of humans with technology. So the technology kind of enables this cycle, and the more effective the technology is, the faster we co-evolve. And you can sort of imagine and see over time that we've accelerated in our ability to innovate and create inventions. In fact, a common complaint among scientists today is that there's so much innovation going on that we have to become increasingly focused in our fields, and it's impossible to retain a complete awareness of what else is going on. So I want to introduce this idea. So, for a human to add a couple numbers together involves some simple symbolic processing. Usually it's a memorial process. We memorize a lot of these things, and it's not too hard to do. But if you ask someone to add together two very large numbers, then all of a sudden it gets a little more difficult. We don't always remember what the numbers are, or we're trying to go through and we lose track. So we need a more persistent memory, and we take a piece of paper, and that becomes an extension of our own cognitive process. And some people think about this as a coupled cognitive system. In other words, it's not that it's a human cognitive system using a piece of paper, but that it's a cognitive system that combines the human's processing with the memorial, the persistent memory afforded by the paper. And of course this requires a very simple piece of technology. So I think the larger vision here is that what we're aiming for is a coupled cognitive system where life processes and machines are working together to do reasoning, and that the physical universe becomes our state space. The physical universe is that piece of paper. It's the memory chips in your laptops. It's all the written books that exist. Everywhere that we're storing the information, it could be the more ephemeral activations in your brain. That's the substrate. But whether it lives in our brains or it lives in a computer or it lives on paper, it's all part of this coupled system. And as we build out these collective systems, and they're interacting more with the physical world in different ways. And we have the Internet of Things, so we have sensors in the world that are feeding into this system. And we have actuators in the world that are then changing the world in different ways. And then we have immediate feedback from humans and other sensors and things. You start to get this kind of this organismic quality to a collective kind of behavior. And at first, maybe this is what our predictive model of the world looks like today. And as these systems become more effective and complex, we hope to build more pristine models of the physical universe. And so, in a sense, it's universal self-discovery. We're part of the universe. Our minds, our brains are part of the universe, and we're self-modeling. And through the self-discovery process, and by developing this better self-understanding of at least the part of the universe we know about, we hope to derive a survival advantage that will allow us to at least survive the problems we've created for ourselves. So when you think of a brain and you think of the neurons in a brain, they're not that complex. They're not that sophisticated. But when you think of a collective system, the real challenge there is that we're not just building a network of nodes. We're building a network of networks. And the kinds of processing that goes on, not in all cases, but in many cases, are more complex than what a neuron is doing. And so I think one of the great challenges that faces us in this field of crowd science and human computation is how do we build an effective network of networks? So AI might be the next level of information processing, or some combination of artificial intelligence and humans. But for the time being, I think that there are opportunities that exist today for us to solve problems where humans can be an important part of that loop. So, thanks for listening.
Zapraszam głosem. Świetność.
I have one. Actually, I'm kind of interested in using humans for problems, yes, but how can you solve the certain pathologies such as trolls and cognitive biases? We know that some have confirmation biases, some have explicit emotional appeals to certain models and such. How do you solve that problem? Do you exclude those people or just try to make a different predictive model?
That's a great question. So if I understood right, the question is, how do you solve the problem of basically the vagaries of human behavior and cognition, that some people will be more or less reliable than others, and they can be very unpredictable. Is that the question? So we actually, in the Eyes on Owls project, we encountered this issue. This is the crowdsourcing the Alzheimer's research. Because people like to build web bots and try to rack up a score. It's a challenge that some people enjoy, and certainly we've noticed there are differences, that some of the people volunteering always tend to classify one direction or the other. They have a bias, as you said. And we wanted to build a platform so that people with Alzheimer's disease or early stages of Alzheimer's disease could participate. And one thing we know about Alzheimer's disease is that there are fluctuations in cognitive ability. And there's the sundowning effect in the afternoon where there's a cognitive decline during a certain part of the day. So we actually, this is sort of the science of what we do, is to investigate different approaches to handle these situations. And one approach is sometimes called wisdom of crowds. So we combine many answers to come up with one very expert-like answer. But there are, a dozen ways you could do that. What's the right way? And part of what we're trying to do is figure out the answer to that question. And we borrowed from the psychophysics literature, and we used actually radar theory to do this. So signal detection theory, the idea that you can look at the performance of a decision-making system, and you can tease apart sensitivity and bias. And then we could just establish profiles for the volunteers, and but it wouldn't be enough to have a growing static profile. We know that there's fluctuations over time, so we use a moving window. And so we actually assess bias and sensitivity in real time, near real time, with our volunteers. And then when we combine their answers, we take into account these things. We use a weighted average, and we account, we don't yet, but we will account for the bias, or this is an evolving approach. But so far, we've actually been able to improve the efficiency of our system without any loss of sensitivity or specificity, from having to have 20 people answer about the same blood vessel to now we only need 7 people to answer it, using this approach. And I think what human computation allows us to do is enable a coevolution of machine-based and human-based systems. And keeping humans in the loop on those systems is probably not a bad idea for lots of reasons. And I always say you always need a kill switch. Any other questions?
So I have one question. At some point of your presentation, you connected information processing with life. Is that correct?
Yes.
So you just put the equal sign between
Yeah,
information
it's all it
processing
takes.
and life.
Yeah.
So don't you think that the information processing could occur in different systems other than in other systems which we do not consider as living systems?
I've wondered about that myself. I haven't thought very deeply about it. What do you think?
I have no idea. I know that the information exists because the information is a part of quantum thermodynamics, and essentially as an element of objective reality exists. Whether the information is being processed, this is a little bit more kind of a subjective thing, which we relate to with some living organisms. So.
Yeah. So I think that, I like the way you kind of describe that. So maybe there's a distinction to be made between data and information. So the thermodynamic data is out there, but in order for it to become information, it has to support some goal-directed behavior, right? This is the way that I think about it. Information means it's informative. Well, to be informative, it has to inform something. It has to inform a decisional process. this becomes philosophical, right? I mean, does information exist in a vacuum?
Well, one of the biggest problems related to the black hole, the origin of the black holes, is related to the
Yeah.
information. Actually, the law of conservation of information is assumed to be existent in nature. So I believe the information is a part of the objective reality, information. And you cannot destroy actually information according to the modern cosmological ideas. But whether the information could be processed in the systems other than living systems, as you pointed out. It's a big question.
It's a big question. Maybe you can help me figure out how to use black holes to help solve societal problems.
My question about machine and human convergation in the ideas of Gerd. Do you know Gerd Leonard? And the concept technology versus humanity. Machine, if you please, by these pictures, ideas, by these pictures. Your comments.
Oh, okay. Thank you. Okay, so I don't have a way to project this. So let's see if I can verbalize. So I think it's in some ways similar to your question. So technology versus humanity, and now the machines are helping us, and so the machines are helping us, and we're happy about that. But then what they're really doing is kicking us out. And so the conclusion here by this person is that successful organizations will need to master both. And they show the yin and the yang, algorithms and technology, and humans and humanity. And so I would say I agree. Anything else? I'd love to hear. Yeah, I mean, I know you're a lot of really smart people. So, and I really welcome critical comments as well. Well, thank you very much.